Aloha and welcome to our video on ocean circulation. In this video, we'll explain how surface currents develop. We'll describe how ocean currents can affect climate. We'll state the importance of upwelling, and then we'll describe the formation of density currents. Okay, so let's take a look at our ocean surface currents. And as we look in this diagram here, you can see that we have several different named currents. These are the big ones that are always going to be flowing. Now, currents are going to be primarily formed from two reasons. It's either going to be wind, okay, which are these large surface currents, and then when we talk about some smaller currents, we'll talk about how waves can induce a current as well. But for the most part, these are going to be generated by surface winds, and our surface winds are going to be influenced by what we call the Coriolis Effect, and we'll talk about that a little bit more in the next slide. But what you'll notice is, remember, the Earth is always spinning. So as the Earth is spinning this way, what we're going to notice is where you have an area where there's not a lot of winds, as the Earth is spinning, it's going to leave the water behind, and that's what we notice here at the equator. And all of the equator, we're leaving that water behind as the Earth is spinning, and that causes the equatorial currents. And most of our equatorial currents are going to be flowing from east to west. Now, as these equatorial currents, and let's just focus here in the Atlantic, it's going to travel this way, it's going to run into South America. And as it runs into South America, that's going to cause it to bend around, and we end up going up the coast of North America with a warm current. So we're going to have warm water from the tropics coming up along the coast of the Americas. And then that's going to shoot across the Atlantic where it'll cool off, but it's still relatively warm until it gets cool up here into the North Atlantic, and then we'll have a cold water current travel down. And you can see how we form these circles or these gyres, and this is the North Atlantic gyre. So on the Atlantic Ocean, we have this warm water traveling up, so our beaches are going to naturally be a little bit warmer, versus if we go to California, where we're on the east end of the basin, we'll notice that warm water is traveling up across here, it's cooling off, and we have a cold water current coming along California, and that's why the waters in the Pacific, on our Pacific coast, are going to be a little bit cooler. And we can see that that'll come down, the Peru current will come up, those will collide, and that's what causes the equatorial currents to be moving from east to west as well. Okay, so let's talk about the Coriolis Force. The Coriolis Force is an effect of the Earth rotating, okay? So if we take a look at a non-rotating Earth, if I had a projectile like a baseball and I threw it from the North Pole to the equator, it would travel in a straight line. It would travel straight south to the equator, okay? And that's what we would see. However, we have to remember that the Earth is rotating. So remember that it's going to rotate this way. As it does so, that non-attached particle, that baseball, is going to have this bend in its motion. It's apparent. It's still going to travel in a straight line, but it's going to look like it's bending this way because the Earth is rotated around it. So here, while I was throwing it and aiming for the target, in the time that it got there to go, the Earth had rotated 15 degrees, so it gives an apparent motion that it is bending or curving like this. And in the northern hemisphere, it's going to curve a little bit to the right. So if we take our map, and this is going to be a really crude map, here's North America, and over here is going to be Europe, okay? Remember we talked about our currents, okay? So we have this warm equatorial currents caused by the Earth rotating. Remember, the Earth is going to rotate this direction, so this water is left behind because water is not attached to the surface, so we get this westerly looking current going here. Then it's going to slightly curve to the right, so in reality it's going to kind of go like this. So now we can see why it goes up the coast of North America, and as it travels up the coast of North America, that Coriolis effect is going to cause it to bend a little bit to the right, and it's going to travel across the Atlantic Ocean here, but really it's going to kind of have that curve still. And here we get cooling off, we get this cold water current going down, and that's going to kind of turn like this, and that's how we build our North American gyre. Okay, this current in North America, this one right here that we see coming up, we call this the Gulf Stream. And let's take a look at the Gulf Stream. So in this picture here, let me show a couple things. Here we have New York, here we have Washington, D.C., here we have Norfolk, Virginia. So we can see the coast of North America. We have this cool water from the north that's kind of trickling down this way, but we have this warm tropical water coming up, and this is what we see as the Gulf Stream. And you can see how it's going to carry this water across. Okay, it's going to cool over time, of course, but as it's traveling across the ocean, you can kind of see this warm, this severe temperature variant. So we have this warm water that's flowing, and that's what we call our current. So we can see where the Gulf Stream is by looking at temperature that way. So here what we notice is we have our major ocean surface currents. Each of our oceans are going to have a gyre system in them. The Indian Ocean gyre will be here. The Arctic Ocean gyre is here. The North and South Atlantic, because they have this equatorial current going on, you'll notice there's a North Atlantic and a North Pacific gyre and a South Pacific and a South Atlantic gyre. And you can imagine the water temperature is going to be based on where it's at. So if we look at the Indian Ocean gyre, you have this cold water flowing up this way. You can kind of see this cold water flowing up this way from the Antarctic region. As it gets into the tropical region, it's going to warm up. Now we have warm water, and that warm water is going to flow down and either come around this way and cool off again and continue this Indian Ocean gyre, or some of it will escape out this way, and then we can see that it'll move that way. And we'll talk about how all of these currents kind of tie into each other a little bit later on. Okay, so let's take a look at upwelling really quickly. Upwelling is going to be caused primarily by these surface winds, and these surface winds are going to take this warm surface water and it's going to blow it away from an area. And as it does so, it leaves behind this little empty space. So this little emptiness is going to be here, and the only place that we can replace that with is going to be this deep, cool water is going to get pulled up into this space. So you can kind of see how that cycle will continue there. So as these surface winds are blowing, this upwelling occurs, and upwelling is where we're taking this deeper, colder, nutrient-rich water and we're lifting it up to the surface. And that allows for these nutrients to be there, and we can see phytoplankton now has the nutrients, so we can see photosynthesis occurring. So where we have upwelling, we generally will have areas where we have an increase in productivity because we're bringing up these nutrients for photosynthesis to occur. Okay, what this picture is going to show us is it's going to show us some of this deep water circulation caused by density. And if we notice, we have this warm water up at the surface that's going to cool. And as it cools, we're going to notice that it becomes more dense. It's going to plunge downwards. And as it plunges downwards here, what you'll see is it'll run into several different things. In the Antarctic, this is the south here, our Arctic is the north up here, we have this really cold water that's always going to be cold. And we'll notice that this water here is going to flow and kind of try and fill the ocean's bottom this way. When we have our Arctic waters are going to collide into this, and it's going to cause it to kind of move upwards. And as it does so, some of it will cool here and it'll form into this Antarctic bottom water, but some of it will come up and it'll form this Arctic intermediate water level here. So now we have it warming up, and as it warms up, it's going to get cool again and come down, but we'll also see this area here that's going to start to circulate as well. So we can have deep water movement of water, mid-waters movement, our surface waters at the equator. What's going to happen is we get wind currents, surface currents, and that's going to push this water up to the poles. As it pulls up this way, it's going to cool, and that'll cause a downward flow and cause this circulation. If it gets further to the poles, it'll cool further, become more dense, and cause it to sink a little bit more rapidly. So we get this mixing going on at the ocean. Primarily at the poles is where we see a lot of the mixing going on, or in these higher latitude levels. And this is where we kind of saw that earlier, where the ocean tends to be like a uniform layer at these points here versus these strict layered out regions that we see down in the tropics. Okay, in this picture here, we're going to look at this conveyor belt model of ocean currents. And what that means is that all of the ocean currents kind of tie into each other. And what it allows is it allows for global circulation. So if we start off here with a surface current off the coast of California, what we'll notice is that surface current can take it out through into the Indian Ocean, and in fact through the Indian Ocean and up to the North Atlantic, where it'll cool off. When it gets to the North Atlantic and cools, it becomes a little more dense, becomes one of these deep water, subsurface density currents that flows underwater, and this can actually carry us back to the Indian Ocean, and then we can join again, or it could carry us all the way over back into the Pacific Ocean, and we can see joining back with surface water. So you can see how the entire oceans are connected by these warm surface currents and these cooler subsurface flows, these underwater currents, and how they all tie together and they can mix for the entire ocean. So we can see how water can travel from one to the other. They're not isolated areas. Okay, so that's it for our video. As always, good luck on your quiz, and we'll see you in the next video. Aloha and welcome to our video on waves and tides. In this video, we'll describe how ocean waves get their energy. We'll state the 3 factors that determine the characteristics of a wave. We'll describe how energy moves through a wave, and then finally we'll explain forces that produce tides. Most waves are going to be caused by winds. So what you're going to have is this wind blowing across the surface in this direction, and that's going to generate these waves, and that's where we see the direction of wave movement. So even though if we have a lot of wind like a storm here, it's going to start the wave moving, and that wave's going to continue in this direction. And you can try this at home. Just take a bowl of water and a straw and just blow on the surface of the water on one side of the bowl. You'll create waves that'll travel to the other side of the bowl, and that's kind of what we're talking about here. Now, when we're talking about waves, there's a couple different pieces and parts I want you to know. We have a wavelength, and the wavelength is going to be the measurement from a point on a wave to the same point on the adjacent wave. So here we're measuring from the top of the wave, which is what we call the crest. And if we go from the crest of one wave to the crest of another wave, that's going to give us our wavelength. Now, the crest is the high point, the trough is going to be our low point, and the difference between the crest and the trough is what we call our wave height. Okay, so that's what we're looking at for properties. You kind of want to know the wavelength, the crest, the trough, or the wave height. If we notice on the surface, because we're moving these particles, notice we have these circular orbital motions. We're seeing this water particle is going to travel in these circular paths. Notice the water doesn't move. What we're seeing is the water moving in an up and down manner rather than continuously moving in one direction. And I know that's contrary to what we said a little bit earlier in things like upwelling, where we're moving the entire water. But here we're just talking about how that wave can be propagated and how it continues and travels across the ocean. Okay, so let's see what happens with a wave when it transfers from deep water to the shore. And deep water, notice that the range of depth that the wave can actually impact the particles is constant. It's not hitting anything, it's out in the ocean. Notice all the waves are kind of uniform in wavelength and wave height. It kind of works that way. As they get close to shore, this circular here, these circular motions, this depth that the wave can travel through, this energy disturbance starts hitting the bottom. And as it hits the bottom, it drags across the bottom and it causes the bottom part of the wave to slow down. And we can see here we have a nice uniform wave, but as we're starting to drag, you start seeing how the top of the wave is able to move faster than the bottom of the wave. And ultimately, that's what causes it to break on the shore, which is what we see. So that's pretty much waves. Most waves, like we said, are going to be caused by winds that are blowing across, and they'll cause these disturbances. And as these disturbances get close to shore, the bottom of them starts dragging on the shore, and we see these waves breaking. Okay, let's move on to tides. Now, the biggest force that causes tides is going to be our friend the moon out here. And the moon has gravity, the earth has gravity, and if the earth's gravity is pulling the moon's gravity is also pulling the earth. As it does so, it's able to pull the water, and we're going to cut the earth in half. Okay, we're going to cut the earth in half this way. And it's going to pull the water on this side of the earth here to form this little tidal bulge here. We'll notice that bulge there. Okay, so this is where we're going to have high tide because there's that bulge there. And then where there's no water is where we would have a low tide. Now on the opposite side, we also notice there's this bulge. And the reason we have a bulge on this side is because the earth itself has been pulled and left some water behind. So we have the tidal bulge on the side of the moon from where the water's being attracted, and then this tidal bulge on the opposite side of the earth where the earth is being attracted and left the water behind. So that's why when we look at our picture, we have our earth here. We're going to have a tidal bulge on the side of the moon, and we'll have a tidal bulge on the opposite side. And then these are our areas of high tide. Okay, so this is where we have a high tide here. And where we don't have the water is where we're going to have our low tide. Okay, So we can kind of see it that way. Now remember, the Earth rotates, so as the Earth is rotating, it's rotating through these tidal bulges, and that's how we have a high tide and a low tide going on throughout the day. Now you'll often hear when we're talking about tides, and in the lessons, you'll hear of what we call a spring tide and a neap tide. Okay? A spring tide is where we have a pronounced tide. So notice here, we're going to look at our picture. We have the sun here and we have the moon here. Now remember, the moon causes the lunar tide. Lunar is going to refer to the moon, and that's where we have the biggest bulge of water. But we also have a solar tide, which is caused by the sun. So even though the sun is so far away, remember, it's so massive, it has such a force of gravity that it's going to create a little bit of a solar tide as well. In a spring tide scenario, when we have a new moon or a full moon, notice how the moon is lined up with the sun and the earth. So we form this solid line that goes through all three objects. In this case, that means that the lunar tide is being added to the solar tide, so we have a pronounced, a larger tide, and that's what these spring tides are going to be. Okay, so that means that if we look at the earth here, we're going to have the solar tide, which is going to be a smaller bump here, but added to that the larger bump of the lunar tide. So because both of them are together, it's going to be a greater tide, and that's what we call our spring tides. Now, we notice here we also have a neap tide. In a neap tide, we have our line from the earth to the sun, but our line to the moon is going to be perpendicular to it. So now we have the pulling of the lunar tide here and the pulling of the solar tide here, so we have less going on. If we were to draw this, we have our earth here, we're going to have our solar tide bumps here, and then we'll put in our lunar tides here, and notice that it's not as pronounced as it was in the spring, so we have less tide, and that's going to be our neap tides. So spring is when everything lines up. Neap tides are when we have this perpendicularity going on right there. Now we can define the tidal pattern by how often we have a high and a low tide in a 24-hour period. So notice here we have the diurnal tide pattern. And the diurnal tide pattern means that in a period of 24 hours, we have exactly one high tide and one low tide. Okay, we also can have a semi-diurnal tide pattern, and this one in the same 24 hours, notice that here we're going to have two high tides and two low tides. Okay, so it happens in a semi or a part of a day. So this is a full day tidal pattern, this is a part day tidal pattern. And then we end up with also a mixed tidal pattern. And in a mixed tidal pattern, notice that we are going to have our two high tides and our two low tides. But notice how we have a significant low, we have a low, we have a high, and then we have our significant high. So it's going to be kind of mixed in the highs and the lows, but it's going to run on the semi-diurnal pattern. Okay, that's it for our video. As always, you'll get more information in the lessons. Good luck on your quiz, and we will see you in the next video. Aloha, and welcome to our video on shoreline processes and features. In this video, we'll explain the forces that act on the shoreline. We'll describe how erosion contributes to the formation of a shoreline. We'll also see how deposition can contribute to the formation of a shoreline, and then we'll end talking about a way we can stabilize the shoreline. Okay, so let's look at some forces that are acting on the shoreline. Perhaps the most common one is going to be wave impact, and that's just the waves hitting the shore. That constant hitting can cause some weathering, but also the waves moving up and down the shoreline can take away sediments, and that would be erosion. So we can see a lot of impacts of these waves hitting the shoreline and causing the shoreline to change. Now, a little bit less known or a little more subtle force would be abrasion. And that's going to be as these waves are coming along or as the currents are traveling along the shoreline, you're going to be moving sediment with it. And that sediment's going to have the ability to bang into things and break it down and to crunch it out that way. So it's kind of like if you sat on the ocean shoreline and a wave came up, how it's going to move some of the sand with it. That sand has the abrasive properties that it can grind away other materials or itself, and that'll cause some weathering, and ultimately erosion will happen with the wave action as well. Now, we also can kind of see wave refraction. What that means is as the wave comes in, it's going to hit these points here first, and then this wave is going to kind of bend around as it travels this way. Okay, so we're going to see a little bit of changes in the way that it's going. It's going to kind of stretch this wave a little bit, so the impact here might be a lot less than it is here because we have a lot of that energy has gone into bending that wave around a little bit. So sometimes we will see more weathering here and then deposition going on here. Okay, and then finally we have this longshore transport, and it's from these longshore currents, and that means that as the wave is coming, notice our wave isn't coming straight in, it's coming slightly at an angle, and as it continues to do so, it's going to push this water, and that's what causes this longshore current, and that can carry away material. So we can see erosion that way, or it can change the depositional pattern as well, how that material is being put back down. So let's take a look at some erosional features. Here in our picture, we're going to have our normal shoreline here, our coast, and it's a rocky shoreline, so it's going to be kind of a cliff. And what's going to happen is the waves are going to be coming here. Between high and low tide, this is the area that's going to be affected the most. Waves are going to constantly hit here. Sometimes it's going to be the wave smacking, sometimes it's underwater, and that's going to allow us to have these cuts here. As those cuts continue to grow, we're going to have some overhangs. Okay, we're starting to form a cliff here. We're going to see that this part here can collapse down into the water, and as it does so, the wave action is going to carry it out to sea, and we can start to build these platforms like you see here. And then we also have these wave cut cliffs that are going to get pushed back further and further and further. So we kind of see this when we have a rocky, like a bedrocky type shoreline. All right. Now sometimes we'll notice some other things. These rocky shorelines can be separated out, and you can have this point coming out into the water. Let me change here. We'll come this way. You can have this point going here, and it's going to be embedded in the water. Now, this can get cut from the shoreline, so that's what we'll do here. We'll cut this one out here from the shoreline here, and what happens is the wave action is going to go, and as the wave action is going, we're going to see erosion and deposition occurring more here, a little more pronounced, and we end up with something that's going to look like this. And this is going to be our sea arches here. So we can see how that would happen from the waves. As the waves continue, you're going to see a little bit more chopping here, and as that chops here, it's going to cause bigger pieces to go down here. And ultimately, we can end up with just a pillar, which is what we call the sea stacks. So a lot of times we'll have our sea arches, and as the arches collapse over time, you can see these pieces here are going to fall down into the ocean, and ultimately it'll break, and we're left with what we call a sea stack. Now we can also have shoreline features that are caused by this deposition, okay, this laying down of sediment. And that's what we want to look at in these pictures here. We notice the first one we'll talk about is a spit, and these spits here are going to be just kind of like where it continues out a little bit. So if we have a longshore current coming down here, it's going to deposit this stuff, and it gets to the edge of a bay or the edge of a river, and it's going to deposit it here, and not so much here because it can flow in and out and around, but there's nothing for it to deposit it onto. It's going to be deeper water. And eventually we can build up these spits and come across. Now, if we have enough of the spits going across, then we form what we call a sandbar. And the sandbar will actually close off the bay and cause it to form a lagoon. And if it's not fully attached, then we have what we call a barrier island out here. Okay, so that kind of relates how we get our spits, our bars, and our barrier islands. The next is this tombola. The tombola is a little bit different, and that's where we have this deposition going on here, where we're going to build up this sand, and instead of making a sandbar that closes a lagoon, we're going to have this sand deposition that's going to connect an offshore island to the shore, and that's what a tombola is there. So you can kind of see it pictured here. Here's where we would have had our island, and the deposits are going to line up here, so it kind of connects an offshore island to the shore with deposits. Okay, finally we're going to talk about stabilizing the shore, and that's important because we want to keep our beaches and we want to keep our shorelines. We can do this two ways, through protective structures or through beach nourishment. The protective structures we can build, probably the easiest is a breakwater here, or a seawall, which we'll see here, and what that is that's putting something that's going to be solid in the way. The breakwaters generally will allow the waves to break upon them, and then the area behind the breakwater is going to be sheltered and protected. Okay, so that's what a breakwater does. A seawall is where we're going to build that structure on the shore, and that allows the waves to hit something that's not the shoreline. Okay, so it'll protect it that way. We can also build a jetty or a groin. They're both about the same thing. Jetties generally are going to be around a harbor entrance, a river exit, a bay, something of that nature. A groin's just going to extend out from the shoreline. Both of them are going to stop this sand movement coming from a longshore current. So what will happen is as this current is flowing and carrying these waters, it runs into these projections, and then it'll slow down, and that'll cause deposition to occur. So we see the sand laid out that way. So that's one way that we can actually protect the beach and we can maintain that shoreline. The other way is through what we call beach nourishment. And beach nourishment is where we will actually bring sand back to a beach. So if you look at an area like Waikiki Beach, which used to be a swamp, there was no sand, so they came in and they deposited sand there, and they continuously do so to put more sand so that they can preserve a beach that everybody will come to. So you can see the financial importance of stabilizing a shore in that example. Okay, that's it for our video. As always, good luck on your quiz, and we'll see you in the next video.